temperature is our next topic. What is temperature? Temperature is not necessarily a simple concept. We can use a simple model for ideal gases, though, so this is why we love to use ideal gases. Temperature, the concept becomes very simple. Now, when two objects are in contact, energy moves from the object of high temperature to the object of low temperature. And let's try to just draw a little model of how that might work. Here is a cold object right here at temperature T cold. And right next to it, I've got a hot object at temperature T hot. And what happens is molecules in this object right here, they are moving fast. I'm going to draw that little velocity vector. They've got big velocities. And what happens is they will impact molecules on the cold object right here at where the interface is. And just like two objects colliding, it'll give that object, that little molecule, some kinetic energy. So when molecules that have high velocities over here hit molecules of low velocities, they tend to collide with them and give them higher velocities. So the general energy flow is this way from the hot object to the cold object. That is the direction of net energy flow, because the energy is moving from the molecules of high kinetic energy, the fast-moving ones, to the molecules of low kinetic energy, the molecules in the cold object. Now, it is true that occasionally a molecule from the cold temperature object may impart energy to a molecule from the hot temperature object. An individual molecule collision could send energy the other way, but on average, the net energy flow is always from the hot object to the cold object. The reason that net thermal energy always travels from hot objects to cold objects is due to probability. Fast-moving molecules cover more distance per unit time, so they're more likely to have collisions than our slow-moving molecules. Hence, fast-moving molecules are more likely to transfer their kinetic energy to other molecules. They're more likely to collide and to give away their energy. If two objects are the same temperature, when they are placed in contact, there is no net energy transfer between them. That is how they are considered to be at the same temperature. In fact, that brings us to the next topic, which is the Zeroth Law of Thermodynamics. It's kind of a humorous name, the Zeroth Law, because it kind of precedes the other laws, the first, second, and third laws of thermo that we will study very soon. But it's simply a way of explaining the meaning of temperature, which is, again, it's not that simple, but this gives us a way to explain what temperature is. And simply put, when two objects in contact no longer transfer any net thermal energy to one another, in other words, when there is no net flow of energy from one object to the other object, the net flow is zero. That means they're at the same temperature. We call that thermal equilibrium. There's the same amount of energy leaving an object as going into the object. So two objects in thermal equilibrium have no net flow of energy between them. They are at the same temperature. Now, the Zeroth Law of Thermo specifically states, if object A is in thermal equilibrium with object C, and object B is in thermal equilibrium with object C, then object A is in thermal equilibrium with object B. In other words, they're the same temperature. Now, let's see what the heck that means. So let's say I have an object right here. Object A. And let's say it's in thermal equilibrium with another object. Here's object C. So if object A is in thermal equilibrium with object C, there may be energy flowing back and forth, but it's the same amount of energy flowing out of A into C and flowing out of C into A. So those two are in thermal equilibrium. If object B is also in thermal equilibrium, let me draw object B in here. Here's object B. If it is in thermal equilibrium with object C, then we say that, so A is in equilibrium with object C, B is in equilibrium with object C. We can state that object A is in thermal equilibrium with object B. In other words, object A and B have the same temperature. So this is a way of describing what temperature is. It simply means that objects of the same temperature right up next to each other, there will be no net flow of energy from one object to the next. That is a one way that we can kind of explain what the meaning of temperature is. Now we get to the fun part, which simplifies this whole thing a whole lot. Temperature in ideal gases. A lot simpler. In ideal gases, the internal energy, U, is entirely in the form of translational kinetic energy. Ideal gases, remember, are just point particles. So for ideal gases, temperature is directly proportional to internal energy. So if an ideal gas has a higher temperature, it's got a higher internal energy. So the master equation for thermo, which really kind of puts everything together, we're going to derive this later, but here's the master equation. The internal energy of a gas is 3/2 times N, which is the number of moles of gas, times R, which is the universal gas constant, times the temperature.
In Kelvin.
So you can see that the internal energy is proportional to the temperature directly. You might also notice that it's proportional to the number of moles. If you have 2 moles, in other words, if N is 2, at the same temperature, it'll have double the internal energy, simply because it has double the kinetic energy. And R doesn't change. R is a universal constant, so that doesn't change ever. We can also write this way. The internal energy is 3/2 times big N. Big N is the number of molecules in a gas sample, times K sub B. K sub B is Boltzmann's constant, and we'll discuss the meaning of both R and KB later. Again, times T. These two equations are very, very closely related, and if you look closely right here, you might guess this combination N times R is equal to what times what in another equation? Well, if you just look at the parallelism here, the number of moles times the universal gas constant is equal to the number of molecules times Boltzmann's constant. So as we'll see, the Boltzmann's constant is just the universal gas constant divided by Avogadro's number. We'll see that much later.